In this deck, we focus on a yard-side problem that directly controls how smoothly export loading will go later. Pre-marshaling. Export containers are stacked in bays, and the stacking pattern determines whether the yard crane can retrieve the next required container immediately or has to perform extra reshuffles. The goal of pre-marshaling is to proactively rearrange containers before vessel loading begins, so each stack follows a clean priority order from bottom to top. If a container that must leave sooner is buried under a container that leaves later, the terminal pays for it in extra moves, longer loading time, and higher vessel delay. The scenario is the export yard at the Port of Shanghai. Containers are stacked in bays that can reach up to 6 tiers. Containers have different departure schedules, ranging from tomorrow to weeks later. The operational issue is the miss overlay. A higher priority export container sits below a lower priority one. A concrete example is a bay where a container that must depart Monday sits beneath a container that departs Wednesday. When Monday arrives, the operator must move the Wednesday container first, just to access the Monday container. These unnecessary moves can cascade and, in severe cases, can roughly double the total handling time. Pre-marshaling aims to eliminate these misoverlays in advance, and can reduce total handling moves by roughly 40 to 60%. We solve the yard pre-marshaling problem through a tiered toolkit. Tier 1 provides a network flow formulation that identifies minimum cost repositioning moves under feasibility and ordering constraints. Tier 2 uses a list scheduling heuristic that makes fast local decisions by scoring candidate moves. Tier 3 applies particle swarm optimization to search for better solutions using a population of candidate plans. Tier 4 uses deep reinforcement learning to learn a relocation policy over many training episodes. Tier 5 uses a digital twin to quantify end-to-end impacts under weather, equipment, and schedule uncertainty. Tier 9 introduces quantum walk ideas as a roadmap for exploring massive configuration spaces. Tier 1 reframes pre-marshaling as a minimum cost flow problem. The key insight is that you can represent feasible container placements and movements as flow on a structured network. Then choose the minimum cost way to move all containers into a correctly ordered final configuration. Operationally, this formulation is valuable because it gives a correctness baseline. It makes the constraints explicit, one container per position, and a strict priority order inside each stack. Once the formulation is correct, you can benchmark heuristics and learning methods against it. This slide defines the network structure. There is a source node, a set of position nodes, and a sink node. Position nodes correspond to stack and tier positions paired with specific containers. Operationally, this construction lets you encode a container ends up in a specific slot as a flow decision. It also makes it possible to enforce stacking feasibility and priority ordering through network structure and constraints rather than ad hoc rules. This slide defines the core parameters and decision variables. Each container has a priority value where lower numbers represent higher priority. Each allowed move or assignment arc has a cost. The main decision is whether a container flows from one node to another, representing a relocation decision. Operationally, cost can represent physical effort, time, or disruption, while priorities represent which containers must be accessible first when vessel loading starts. The objective is to minimize total movement cost across selected arcs. Operationally, this means you are looking for the smallest number of moves or least expensive set of moves that still produces a yard state where export retrieval can proceed without reshuffles. These constraints ensure that all containers start from the source and end at the sink, meaning every container is accounted for. Operationally, this prevents the model from dropping a container or leaving it unplaced. Every container must be routed into the final yard configuration. Flow conservation enforces consistency through the position nodes. What enters a node must leave in a way that preserves the integrity of container placement decisions. Operationally, conservation ensures the model represents a feasible relocation plan, not a set of disconnected partial moves. This slide captures the two most important feasibility rules. First, each physical position can hold at most one container. Second, within a stack, priority must be ordered correctly so earlier departing containers are never blocked by later departing ones. Operationally, this is the whole point of pre-marshaling. You spend moves now so you avoid expensive reshuffles during loading, when time pressure is higher and vessel delay costs can be severe. This diagram visualizes the node-based network flow representation. Use it to see the mapping from the yard to the model. The network is not abstract for its own sake. It is a way to encode where containers can go and what ordering is allowed, so that the solution is executable. This slide provides a small example with 2 stacks and 3 tiers containing 4 containers. The current arrangement violates priority ordering in both stacks. A representative optimal move set uses 4 moves and produces a final configuration where priorities 1 and 2 are placed below priorities 3 and 4. The lesson is that even small yards can create misoverlays, and the network flow approach identifies the minimum corrective moves. Tier 2 introduces a practical heuristic: list scheduling. The idea is to treat movable top containers as jobs. At each step, you evaluate possible moves and choose the move with the best score. The score is designed to reduce priority violations quickly, while also maintaining good stack utilization and move efficiency. This is the classic trade-off of heuristics. They are fast and deployable, but they rely on local scoring rules that can miss globally optimal sequences. This slide shows the flow. Identify movable containers, score candidate moves, execute the best move, and update the yard state. Operationally, this loop is exactly how yard teams think. At any moment, only top containers are movable, and every move changes what becomes accessible next. In the first code section, you typically see data structures for stacks, priorities, and identification of movable containers. Operationally, correctness depends on respecting access constraints. If you allow moving a non-top container, the algorithm becomes unrealistic. This section typically computes scores for candidate moves and selects the best move. Operationally, scoring is policy. If you overweight short-term violation fixes, you may create new violations later. If you overweight balance, you may delay urgent corrections. This section usually executes the selected move and updates the yard state. Operationally, state updates must track which containers are on top, which stacks have capacity, and how priority ordering has changed after the move. This slide provides a 3-stack example with 2 blocking patterns where low-priority containers sit above higher-priority ones. A representative run completes in 4 moves and produces properly ordered stacks. The key point is that list scheduling can fix misoverlays quickly when the bay is not extremely congested. Tier 3 uses particle swarm optimization to search a larger space of solutions. Instead of committing to one greedy sequence, you maintain a swarm of candidate plans. Each plan can be represented as a vector of target stack assignments. Particles move through the solution space by combining inertia, attraction to their personal best solution, and attraction to the global best solution found by the swarm. Fitness combines priority violations, number of moves, and stack balance. This slide visualizes the collaboration aspect of particle swarm optimization. Particles share information about what works and gradually concentrate on better solutions. Operationally, this helps when many local optima exist. Greedy methods can get stuck, while a population-based method can explore alternatives and escape poor early choices. This slide shows the update idea. Velocity is updated using inertia, personal best attraction, and global best attraction. Then position is updated. Operationally, you can interpret velocity as how aggressively a candidate plan changes its assignments. Proper parameter settings are needed so the swarm explores without becoming unstable. This slide defines a multi-part fitness function. It counts priority violations, counts or estimates moves required, and includes a balance term so stacks do not become uneven. Operationally, balance matters because extreme imbalance can reduce future flexibility and can increase the number of forced reshuffles later. This code section typically initializes the swarm and evaluates initial fitness. Operationally, initialization can include random candidate plans or heuristic seeded plans. Seeding can accelerate convergence. This section typically updates particle velocities and positions, evaluates feasibility, and tracks best solutions. Operationally, feasibility handling is essential. If a particle proposes an impossible arrangement, The algorithm must repair it or penalize it strongly. This slide reports an example with 6 containers and 3 stacks using a 50-particle swarm. Fitness improves from 85.2 to 20.0 by iteration 75, and reported compute time is about 0.15 seconds. It also notes that in the shown case, the initial configuration was already optimal with 0 violations. The lesson is that a good method should also detect when no moves are needed, rather than forcing unnecessary reshuffles. Tier 4 treats pre-marshaling as sequential decision-making. The state is represented as a 3-dimensional yard tensor with channels that include container presence, normalized priorities, a movable mask, and stack heights. Actions move a container from one stack to another, and rewards penalize increases in violations and move cost, while rewarding improved accessibility and final feasibility. This framing lets the agent learn policies that adapt across many different yard configurations. This slide summarizes what the agent observes and what it is trying to optimize. Operationally, the movable mask is crucial. It tells the agent which containers can be moved right now. Without that, the agent would waste effort proposing illegal actions. This slide breaks reward into components: violation reduction, move efficiency, and completion bonuses. Operationally, the reward must balance short-term improvements with long-term success. If it rewards only immediate violation reduction, the agent may thrash. If it rewards only final completion, learning becomes too sparse. This slide shows a deep queue network architecture that uses convolutional layers to process the yard grid and estimate values for relocation actions. Operationally, the convolutional structure matches the spatial nature of the yard. It helps the model learn patterns like misoverlays and good access paths. This section typically defines the environment, initializes the network, and sets exploration behavior. Operationally, training is performed in simulation. In a real terminal, you would deploy a learned policy only after extensive evaluation and safety checks. This section usually selects actions and applies them, storing transitions in a replay buffer. Operationally, replay helps learning stability because the agent can learn from past rare configurations without needing to encounter them constantly. This part typically samples mini-batches and performs network updates. Operationally, stable updates matter. A policy that oscillates between strategies is risky because it can create inconsistent yard behavior. This section often updates a target network and manages exploration decay. Operationally, these techniques are standard safeguards against instability and value-based reinforcement learning. This final part typically evaluates the learned policy and tracks performance across episodes. Operationally, you want both feasibility and efficiency. 0 violations achieved with a low number of moves. This slide reports training on an environment with 4 stacks and 6 tiers with 12 containers. Training runs for 1,000 episodes with target network updates every 100 steps. Average reward improves from -180.3 in early random exploration to +15.8 by the final phase. Reported success reaches 87% with an average 8.3 moves to solution. Generalization success is 92% on unseen configurations, which is crucial for real-world deployment. Tier 5 introduces a digital twin that integrates yard operations with vessel schedules, equipment availability, and external factors. The twin uses a federated simulation architecture, so constraints like weather delays, maintenance windows, and labor shifts can be propagated into pre-marshaling decisions. This is important because pre-marshaling is not isolated. It must align with the vessel plan and resource constraints. This slide outlines the architecture of the digital twin used for integrated pre-marshaling optimization. Operationally, the architecture connects real-time data feeds, simulation models, and optimization engines. This allows continuous updates and what-if evaluations when conditions change. This slide describes different prediction horizons: short-term, medium-term, and long-term. Operationally, the purpose is to avoid over-optimizing the next few minutes at the expense of the next day. Short horizons support immediate move decisions, while longer horizons support positioning for upcoming vessel departures. This slide reports a detailed scenario: 12 export bays, 144 stacks, and 2,400 TEU with 3 ships departing within 18 hours. Without pre-marshaling, loading requires 4,680 moves, and average vessel turnaround time is 14.2 hours, with crane utilization at 76% and weather adding plus 2.3 hours. With digital twin optimized pre-marshaling, 890 pre-marshaling moves reduce loading moves to 2,850, turnaround improves to 9.7 hours, crane utilization rises to 94%, and weather impact drops to plus zero point 0.8 hours. Tier 9 introduces quantum walk algorithms as a way to explore pre-marshaling configuration spaces more efficiently. Container configurations are mapped to vertices of a graph, and valid moves are edges. A quantum walk explores configurations using superposition and interference. An oracle marks zero violation configurations, so the algorithm can amplify good solutions and suppress poor ones. This is presented as a roadmap for future computational acceleration. This slide describes the update step in a quantum walk, which applies operators that move probability amplitude across the configuration graph. Operationally, think of it as a way to explore many move sequences simultaneously rather than checking one path at a time. This slide describes encoding container configurations into quantum states. Operationally, encoding is where practical limits appear. The number of qubits, connectivity requirements, and noise tolerance determine which problem sizes can be handled. This slide describes the quality oracle that marks optimal configurations by a face flip. Operationally, the oracle is the mechanism that tells the quantum process which configurations are good. It is how the algorithm focuses search on zero violation solutions. This slide contrasts quantum and classical walk behavior. Quantum interference can amplify high-quality configurations. Operationally, the promise is faster discovery of good solutions in massive spaces where classical methods struggle. This code section introduces a conceptual quantum walk procedure. Operationally, treat it as an educational sketch. It illustrates the steps, but practical deployment depends on hardware capability. This section continues the procedure, typically defining operators and the oracle interaction. Operationally, the interaction between the walk operator and the oracle is what creates the interference pattern that favors good configurations. This section continues the algorithm steps and usually discusses measurement or sampling. Operationally, measurement is probabilistic. You repeat executions to get reliable solution statistics. This section continues the algorithm, often showing repeated steps of the walk. Operationally, the number of steps in the circuit depth relate directly to hardware limitations and noise sensitivity. This section continues with additional steps and may include tuning or stopping logic. Operationally, you would typically integrate quantum output with classical post-processing to convert a configuration into an explicit move sequence. This final section typically finishes the procedure and returns the best observed configuration. Operationally, post-processing is required so the solution can be executed as real container moves in the yard.